Hello. Hello, Twitch. Long time no see. This is going to be some chill maths again, like it sometimes is on a Sunday. Hi, Herb. Hi, Charlie. First time in chat. Good to see you. Welcome to the show. This is the Sunday chill stream where I just chat a bit about what I'm up to, or we do some maths or something like that. Nice to see you with us. Also, shout out to who am I shouting out? Sean DSL LVV, and Co-Pirate Twitch, and Mark Shalmer, who all followed me while I wasn't live. Charlie saw Quest for Quintic on YouTube. Yay! That was a funny experiment. Hey, thanks for the follow. Hey, Twitch. It seems like the best thing to happen to my Twitch following and the best thing to happen to my YouTube following in terms of numbers, which I try not to care about too much, but in terms of numbers, the best thing that's happened is to just not stream for 2 weeks. Just don't do anything. The Twitch, I've gained some followers. Hello, nice to see you. YouTube, let's have a quick look at YouTube. I find this very, very funny. First off, my YouTube game is terrible because at the moment all I'm doing with YouTube is I'm putting the recordings of this onto YouTube. So my YouTube channel is just like a placeholder of here's me wearing a jumper, and then I don't do thumbnails, so every video is just grabbing a screenshot. So my YouTube channel just looks like this, which is awful. And I'm surprised that any of these have any views. I bet one person asked me if I was going to put the VODs on YouTube because they get deleted from Twitch after a while, which is a bit irritating. There's a single button you can press to transfer them to YouTube, so I press it. I'm a bit surprised they've got any views. To 26 sounds about right. And then I didn't put anything up for a couple of weeks. And the one talking about Cactus Variations has got like 700 views, which is the most views. I don't know if you've been watching this sort of thing, then hi, I guess. Welcome. I don't know what to do. Maybe don't upload so much. So I've immediately, I forgot to upload the PowerPoint one where we talked about PowerPoint. So I immediately uploaded that one and it's going normal. 27 views, normal. I find YouTube very strange, especially this kind of YouTube channel just hanging around. Oh, hi Murray as well. How you doing? Good to see you. I'm all right, thank you. A little bit gravelly, a bit of sore throat. We'll see how that affects this sort of thing. So anyway, if you've joined via YouTube or something, then nice to see you. Welcome to the Sunday Twitch show. We are gonna do some maths. Sorry, I'm just reading chat. I have my Great Wave shirt on. I have my Great Wave jumper. I have my Great Wave mug. We're doing this. I have my thesis on screen, which has the Great Wave in it at some point. Oh, where's the Great Wave? Let's find the Great Wave. Like really near the front. Not that near the front, but really near the front. In the like motivation section. We thought it was really important to have like proper motivation for things. And yeah, that page straight away. So introduction, page 2. Let's put the Great Wave there. Right. Let's get the screenshot. Quite like this one artwork. It's I don't know if you've seen it. It's this woodblock print of a kind of wave. It's not very well known. It's really hard to get merchandise related to it. Anyway, wanted to show you what I've been working on. Wanted to show you what I've been working on recently. Working on is pushing it a little bit. Something that I've been losing a bit of sleep on is there's this one missing bit of logic in my not in a serious way. Let's restart. There's this one missing idea in my PhD work that I'd like to either close the loop and just understand it better, or there's a chance that this turns into an amazing bit of content. Here's the content. Let's assume it turns into great content. Let's design the thumbnail. I guess it's video content. So I have an integral that I can't solve. Why am I putting text on the thumbnail? Nobody puts text on the thumbnail, do they? It should just be a big picture of my face going, oh my goodness. and an integral. An integral that I can't do, but I know what the answer is. That's the kind of punchline. I can't do the integral, but I know, for fluid dynamics reasons, that it really, really should be 32 over 3 to the power of 1 over 4, which is a pretty weird number. It's a weird number, which is a good hook. Maybe that's in the thumbnail. 32 over 3 to the 1 over 4. And I can't do the integral, but I'm pretty sure that's the right answer. So either I would like to be able to just do the integral, and that would be good, because then I'd be done. I would say, I've proved that it's 32 over 3 to the 1 over 4. Or I would like to try and tidy up the route round explaining the fluid dynamics. The fluid dynamics reason is really complicated and not very convincing and goes kind of the long way round. There's also loads of asymptotics in there. So one way or the other, there's possibly, I've always felt that I'm missing sort of a trick by not turning this into perhaps an integral I can only do with fluid dynamics, or an integral that I can't do, but fluid dynamics tells me that the answer should probably be 32 over 3 to the 1 over 4. Yeah, exactly, Charlie. How am I sure that that's the answer? Right. So what do you want me to tell you? Do you want me to tell you about fluid dynamics? Or do you want me to point at the number in my thesis and go, look, 4 significant figures, it's definitely right? Because that's not, neither of those is going to be very convincing. I'm very convinced that it's 32 over 3 to the 1 over 4. Okay, let's start by just reviewing some absolute nonsense to get an idea of how hard this is going to be to explain. 5,000 word explanation says that. Yeah, okay, so here's the problem. So we're solving the Navier-Stokes equations. They're quite hard. And we're doing an asymptotic solution. I need to explain several things there, don't I? What's going on is we're thinking about bubble coalescence, which is what happens when two bubbles, and for my work, the bubbles are spherical, perfect spheres, and they just touch together at one point. I guess I say bubble to mean sphere of air or something surrounded by water or something like that. Which is, I know that's not great, because when you hear bubble, you think soap film floating in the sky with like an inside and an outside and a thin layer of fluid. But all of the bubbles in, maybe we should have called them something different, like voids or something. But that sounds spooky. Okay, I'll try saying void for a bit until I get fed up of saying void. So you've got these two voids, and they've just touched together, and they're going to well, surface tension says this shape has got loads of surface. Look at all its surface. It would be much nicer if that was just one sphere of radius, I guess, something to do with the cube root of 2 times larger than the original one. I've drawn it slightly smaller, which is the wrong way around. Okay, the idea is that in the ocean this is happening all the time. If I show you my sleeves have got this one bit of the Great Wave where there's all these bubbles or bits of foam that have come off the wave, and they're now in the ocean, and maybe they're going to dissolve into the ocean, or maybe they're going to coalesce with each other to make larger droplets that eventually sort of froth up and come out of the ocean. This is one tiny part of that. Obviously, feels stupid showing you the Great Wave and being like, so anyway, they're perfect spheres, but you've got to start somewhere, right? The idea is that you try and understand these things in terms of basic problems. Anyway, so the liquid's trying to get out of the way. You've got these voids in between, or vacuoles. Vacuole is quite, yeah, the void. And we're starting to feel like it's talking about vacuums and they should just collapse because there's nothing there. They're full of incompressible but inviscid fluid of no mass, of negligible mass. Maybe bubble is the right word. I've got fed up of saying void. That was quick. Okay, so the maths that you do is to try and analyse what's going on to the fluid in that kind of thin sheet. There's obviously something else going on around the outside, but early on, when the bubbles have just touched each other, most of the motion is quite near the point where they've touched. There's this effect called inertia, where the fluid all around has got mass. It doesn't get moving quickly. And what we might try and do is solve for what's going on in that thin sheet of fluid in between the bubbles, and see that far away from the point where they've touched, there's not so much going on. Okay. What do we expect? So what we expect is, for live drawing, the bit joining the two bubbles together to get larger, for these to move apart. Bloop. For the kind of bit joining the two bubbles to grow larger and larger, and expand. And you can do quite a lot of maths to work out how fast that happens. It's really fast, which makes it hard to take photos of this while it's happening. And you can do better than that, because you can start to think about the shape of what's going on in this edge. So if I zoom in here, you can start to think about the shape of how the edge kind of rolls up. You've got this bit over here, which is kind of not moved, and you've got this bit, which is rushing backwards, and originally there's fluid over here, which is now all kind of thickened up. This bit's thickened up as that water's got to go somewhere, as it's going out of the way. Now, hello Mouse Nash. Now, there are two things that you can do to try and solve this or work out how fast it happens. One thing is complicated and one thing is simple. The simple thing was done many years ago and gives a really nice answer. The complicated thing is what I want to show you quickly. Hi Thrice Shy as well. Oh, loads of people here. Hey, what's Twitch say? Twitch says, yay, people are here. Okay, so this is rushing backwards and it's gathering up fluid. So what you can do is you can write down the Navier-Stokes equations for the flow inside this thin sheet, and you can try and find out what the profile looks like. I've got some pictures on the left here of how, so OH is the Ohnesorger number. It's something to do with the viscosity of the fluid outside. Rescaled a little bit, it's not important. That's important because viscosity, this internal friction of fluid, is one of the ways that information is transported through the flow. What you see is when you have a fluid with inertia, there's something like a t⁻⁴ region that grows like the square root of time. There's this growing region where the fluid actually started accelerating. A region outside where it's basically stationary. Viscosity is important in that range. Anyway, so you get these different profiles for different fluids for what you expect to see. Maybe it thickens over some region, like so this picture here is showing me that for that particular fluid on the outside, there's this original bubble shape here, and we're expecting to see some thickening nearby. And the interesting one is what happens if the fluid is not very viscous at all, and that's this picture down here. There's a load of rescaling and stuff going on. These pictures are non-dimensionalized in a weird and confusing way that I wish I hadn't quite done. But anyway, here's a picture of this line is mostly the kind of curve of the original bubble. We've got air in here or something, and we've got water in this bit. And it's mostly minding its own business. It doesn't know what's happened yet. Mostly it's just exactly where it was when it started. But there's this bit over here. Can you see this line just jumps up? And there's this kind of flat, or not, there's this kind of scrunched up region over here where the water's being pushed by the force of surface tension, and in some cases for an inviscid fluid it tends to just sort of pile up. A little bit like, I don't know, it's a little bit like driving a snowplow. let's think about that analogy. What do snowplows look like? I guess they've got a thing like this. They've got a thing like this, and they've got tracks, haven't they? So I need to draw something of tracks. I think I had a little snowplow toy when I was a kid. There we go, and it's going to be coloured in like that. Okay, snowplow. You've got a snowplow and a whole bunch of snow ahead of you. So this is representing force of surface tension as it is sort of pushing all of this liquid. And there's some snow. And you can imagine maybe depending on how powdery the snow is or how solid the snowdrift is, and what you might see is you might see all of it start moving and just all sort of like, okay, I guess it piles up a bit ahead some quite large distance of the snowplow, but somehow maybe if the snowplow is going really fast, or maybe if the snow is not some particular property, then it might all sort of pile up in front of the snowplow. Just doesn't have time to get out of the way forwards, so you form this kind of piling up. It's that kind of physics with a really interesting momentum transfer kind of thing going on in here. Navier-Stokes equations are just brilliant. Anyway, keeping track of what's going on with all of the snow ahead. Okay, so summary then. We've got this kind of simple idea about what happens in a very inviscid case. Not much viscosity, not much internal friction. Fluid just sort of bunches up near the edge. There's a paper that calls this the kind of Pac-Man shape, because you've kind of got, maybe here's your fluid and you've got Pac-Man, and Pac-Man just sort of moves along gobbling up dots of fluid, and they all accumulate at the edge into this thing. I guess that's more like Snake, right? Because in Snake, the snake actually gets larger as it eats stuff. In Pac-Man doesn't get bigger. Anyway. The diagrams people draw are like circular blob. Here's the initial bit of fluid. Here's the blob that's moving along. And there's a thing called the blob model. A lot of people say, aha, fluid at the edge, it's going to move, it's got some mass. We can just do kind of basic physics to say, well, I know what forces there are. I know the mass is changing with time. I know the velocity. So I can do this kind of forces the change in momentum for this blob. Yeah, why not? Why not, right? You got a blob, you want to model it. Blob model. Excellent stuff. Top tier content. Yeah, I know. Super stuff. So this is a really successful model in the sense that it gives you a thing you can actually solve that does quite a good job of explaining what people actually see when they look at dropped bubbles of air in water coalescing. Water doesn't have much viscosity, it's not very sticky. Why am I telling you these things? And that means that this is quite a good model. The result that comes out of that is absolutely brilliant. The result is you expect the growth rate of this gap in the middle to be, let's see if I can get this right, so radius of hole joining the bubbles is something like, am I going to get the gammas right? The gamma A over rho to the 1/4, T to the 1/2, I think it's that, 32 over 3 to the 1 over 4. And the maths to do that in the kind of YouTube video or whatever this is, the maths to do that is not too hard. It's a bit harder than A-level mechanics, and I've just realised what I said out loud. That's terrifying, right? It's like A-level mechanics, but also 3D-ish. It's kind of 1D, really, but it's a bit harder than A-level mechanics. It's like a hard step question in the mechanics section of STEP. Yeah, okay, I've learnt my lesson. Don't do over-ambitious content. Nobody wants that. Like the medium STEP question in the mechanics section to get this number out. Worth it. Okay, so that gives you number 32 over 3 to the 1 over 4. The other thing that you could do is you could ask, well, what happens if I've got a little bit of viscosity? And that's what these pictures are supposed to be showing, to say what's going on if I've got some viscosity. And normally you can't really get away with that. That makes the problem too hard. Normally people work on things that are either so viscous that you can ignore the effect of inertia, or so not viscous that you can ignore viscosity. It's quite hard to do theoretical work on problems with a bit of both. I guess this one does the same thing. 10 to the minus 3 does the same thing. 10 to the 1 does the same thing. 10 to the 0 is a little bit hard to do theoretically. These are numerical solutions, but still. Except in this particular problem, everything balances really nicely. There's just some gorgeous mathematics, which means that loads of things cancel out and it's possible to do the maths. And this was some work that I did. And the power of that is then you've got a solution. You've got these solutions. You've got this method of solving this thing, not just for very inviscid blob model, but you've also got an understanding of what shapes you should see at different viscosities. So I've got these kind of diagrams of, this one's a little bit better, these kind of diagrams of the profile shape in different cases. I've got this picture, which I really like. So this is Owen's organ number at the bottom there. So kind of viscosity, that's the parameter I picked. And the solid line is what comes out of my very simple model using viscosity and inertia. And then the dots and squares are different hardcore numerical results. And the thing we wanted to check was, when you take our result with, you can put your viscosity to whatever you like, and that's just a point on this black line. It's quite hard to see the black line, right? There's quite a lot going on in this picture, but there's a black line that goes through here, slightly curved. When you put in some sort of small number for the viscosity, you should get the same thing as the blob model. Because they're describing the same fluid dynamics problem. To have not very much viscosity, what should it do? I guess the shape should be like a blob, and the dynamics should be like the kind of step level mechanics problem. And that's what this dashed line is supposed to be. That's the relationship that we should get from the kind of blob model stuff. And it all agrees really nicely. This is not convincing yet. So this is where we get into the kind of asymptotic analysis. You've got viscosity on the scale. And the kind of cases that you might look at are 0, where you get a blob. You might look at kind of 1, which is like hard, see this thesis. And then the way you would try and compare these two, viscosity, no viscosity, blobs, and 1 viscosity, somewhere in between, is to look at epsilon for small viscosity and see what do you see in that case. Because in some sense, with a tiny bit of viscosity, that should probably be about the same as the blob model. Otherwise, the blob model is useless. If putting a tiny bit of viscosity in destroys all of the maths, then the blob model was kind of a phenomenon that you'll never actually see. Whereas on the other hand, having a tiny bit of viscosity in, you then get to use all of my equations, where I've got all of the viscosity effects in there as well, and that is what this horrible section is about. It's trying to take the equations that we've developed for that problem with bubbles coalescing, bit of viscosity, bit of inertia as well, bit of everything, and to say what happens if this Owen's organ number of viscosity is very, very small, much less than 1. And there is a whole bunch of stuff to do in this problem. There is an integral, there is some differential equations, there's some differential equations, there is some stuff coming out here, there's some amazing sigmoid stuff to match it together. So this is where it's sort of at rest out here, and then it's got some stuff in here where it's actually moving at some speed. And then you've got to do another bit of asymptotics, and none of this is going in the video. But you get down to this kind of equation for basically the velocity. Omega here is, I was running out of letters, I guess. Omega here is kind of the, oh gosh, what have I done? I've rescaled the velocity. Velocity is, what an explanation this is going to be. The velocity is like 1/2 eta plus omega over eta e. Definitely running out of letters. And you use some dynamical systems, which just makes me very happy because I went to a whole course about dynamical systems in the 3rd year of my degree, and then being able to actually use some of that stuff in research, hooray. It's one of those times where you do the course, at the time when you're doing the course, you're like, oh, this is very hard, why am I learning this? And then it turns up and you're like, good thing I learned all that. It allows you to say things like separatrix for the saddle point, which just feels very clever. Okay, that gives me some information about what I'm trying to solve. There are some amazing solutions. Oh my goodness, it collapses down into this interesting shape for the profile. And then, horribly, I've got to do kind of a numerical solution. That horrible differential equation I showed you with the ring around it, with the 1/16 in it, I gave that to a computer. It's a one-off differential equation to solve. What we're doing here is basically taking the little bit of deviation. Yeah. Is it an early stream? Or is it daylight savings? There we go. Yeah, sorry about that, Neutrino. Okay, hang on, Mountain Ash. I'm going to teach Mountain Ash separatrix stuff in a moment. We're now at the thumbnail. Because I get down to this number, so I gave my computer like this big calculation to do, but it's just one calculation. And then I gave it a second calculation to do, because I need, out of this, in order to stick everything together, my solution is kind of in several IKEA parts. There's this bit for how the edge is narrowing, there's that bit for how the velocity switch off happens, and there's this bit. Probably, you put it all together. And here's the integral, by the way. So I want to be able to integrate omega prime plus 2 over omega, where omega satisfies, and then horrible dE. Satisfies this horrible differential equation. That's the thing I want. I just think I want to integrate out to infinity. Yeah, I want this number. Which I did with my computer again, because I got my computer to find omega numerically. I have a different equation, I have some initial conditions, just go and find it for me, please. And then integrated it numerically with like the trapezium rule or something. And you get a number. And this feels very unsatisfying, because then you plug everything back together again. And you get, from that numerics, 1.807. So essentially, I've got it down to one horrible differential equation, which I need to solve and integrate, and look at its behaviour in a slightly different way. Not so important, but I need to solve and integrate. And having solved and integrated with a computer, because computers can do those things to solve and integrate, I get 1.807, which is extremely close to 32 over 3 to the 1 over 4, which is what it should be. So this is defense of the blob model. This says even if you put a little bit of viscosity in, you still get something that behaves just like the blob model. The blob model checks out. Sort of the limit as you get close to 0 has the same behaviour as the 0 viscosity blob model. So yes, Charlie's right. The thing we should try to do is solve the differential equation without a computer. Yeah. So maybe the video is not quite the integral I can't do, it's more the differential equation I can't solve. Let's have another look at that differential equation I can't solve. I have wasted several afternoons during my PhD, and then really when I was trying to write up the thesis, to just be like, should I just solve it? Should I just solve it? I've got all this like, then I gave it to my computer, and then I also integrated it with my computer, and I got 1.807. Is that close enough? I should just solve it right, and then say, here's the solution. And I integrated it. It's exactly 32 over 3 to the 1 over 4. That would be the dream. It matches the blob model, we would then say, but defends the blob model in small viscosity stuff. So that's kind of the dream. I've got no idea how to solve this. No idea. Sorry. Right. Okay. Let's copy this out, because let's copy that out. Yeah, it's got double subscript. It's pretty rubbish notation. Let's copy it out onto a blank bit of paper. Ooh. Right. How do I do that? Can I get a blank bit of paper? Sort of. That's gone sideways. How do I get it the right way around? Better. There we go. Okay. So there's a -1 over 16 on the left, which is bad enough. And then on the right, there's a second derivative thing. And to make that worse, there's now two terms. This one is +3 over 4, and this one is +2. I think I've got all that right. Did I miss a minus sign? I might have missed a minus sign. Yep, minus sign at the front of this. -16, 2 3/4. There's a y downstairs. Trust? Yep. Yes. Yeah, it's bubble coalescence again. We were down to this. So we would like to solve with, and then there's some boundary conditions. Because this has got lots of solutions, it's a non-linear differential equation. Yeah, just plug it into the computer. It's not that hard, right? It's even in quite a nice format. If you the second derivative's on its own, so you can rearrange it for that, and then that's the format. That's the format that computers. That's the computer's. That's the format the computers like. You just give it a computer. It's not actually that hard. There are some boundary conditions on the behavior. I've realised it's not important. The behavior. I believe you want y of 0 to be 0, and you want y prime to be like y over 8 for large x. I think there's something like that. There's some sort of nonsense conditions that you can make work. Yeah. There are some techniques you learn in A-level, eventually, for doing second order differential equations with constant coefficients. This is really not one of those. It's also quite non-linear, but I have stared at it for ages thinking, am I just being an idiot? Is it just... at some point I'll realise you can just add 3 to both sides or something, and then it's exactly the derivative of something else. I haven't shown this to people for years because I'm really worried that someone watching the stream is going to just tell me, just add 2.5 to both sides and then you're done. My current plan is, this is currently quite nice because it doesn't involve any x. Well, it kind of does in the derivatives, I suppose, but there's no kind of like e to the x over here or something. The current plan is to, yeah. So, but I've sometimes seen non-linear stuff which you can do by separation of variables. I'm maybe not bringing the right level of firepower to this, but non-linear stuff by separation of variables is okay. And I've sometimes seen ones where you spot an exact differential, which is kind of the same thing, but you sort of multiply through by dy by dx or something. It's a bit tempting, isn't it? So if I multiply through by dy by dx, then over here I've got something I can integrate because it's the derivative of minus y over 16. If I multiply by dy by dx over here, I've got something I can integrate because it's the derivative of dy by dx squared over 2. That, if you differentiate that, you get 2 times, oh no, wait, there's a half. You get 1 times dy by dx d2 by dx squared. So multiplying by dy by dx lets me integrate both of these things. But multiplying this by dy by dx gives me some mess that I can't see how to integrate. So the plan of Like some mechanics problems, you just multiply by dy by dx and you're done. That is not what I'm looking at here. You can expand the brackets. Yeah, they're just multiplied together. You end up with things that look like dy by dx squared, though. I don't know what to do with that. Well, I mean, it is what it is. This has some exact solutions, I think. I can show you some solutions that are not quite the right one, but I have some boundary conditions behind the scenes. Yes, maths. You can expand. Okay, right. That is what I'm currently working on, because I sometimes come back to it. I sometimes think there are two things that could happen here. One, I just find a way to do it. I just think, oh yeah, you rearrange it, you flip this upside down and that upside down. You do a substitution like y is 3x plus omega or something nasty, and everything falls apart, and then you're done. That's one thing that could happen. The other thing that could happen is that I get so annoyed by this that I actually make the video integral I can't do except with fluid dynamics. I've tried some random functions. There are a couple in my thesis. Let's have a quick look. Where's the plot? Let's have a quick look. Yeah. So here's the nasty thing. We want the derivative to be like omega over 8 when omega is large and negative. That's for a kind of matching reason. 8's a weird number. I should probably investigate that a bit more. There are some exact solutions, which are shown with dashed lines in this picture. They're mad. They are exponentials. So there's some exponential solutions. I think I have checked exponential solutions in general. I should probably check some more exponential solutions. This red dashed line, which is the thing I'm looking for, looks like a straight line, but I think it's not quite a straight line. Or proving that you can't solve a differential equation. Yeah, I have no idea. It's not really a thing I've seen, I think. Yeah, okay. I think I'll take a course advice and just try more random functions. Right, okay. I think that was... I think that's maybe enough of that. I would like to try something a bit different. Yeah. It's true that you shouldn't expect differential equations to have nice solutions. You shouldn't go into it thinking that you'll be able to write down your solution in terms of nice, tidy functions, which is a similar thing to the quintic fact. Although I'm not aware of people doing any Galois theory on that. I should look into that. Just rule of thumb, you shouldn't be able to expect to solve differential equations. But this one, I don't know, because I know the answer is 32 over 3 to the 1 over 4. It just seems so mad. The other attack I've got, which is to not solve the differential equation, but the other thing I can try and attack is to try and do the integral without solving for the function by exploiting the fact that this is like, so this first bit is like log omega. I know some things about omega. Maybe that'll help me on my quest to integrate this without solving for omega. But what am I going to do with the 2 over omega? So, you know, I have multiple questions that I don't know the answers to. It's just also weird. Perhaps my best use of time would be to take this. This is sort of several levels deep of I did X, Y, and Z to the problem, which resulted in this horrible differential equation. And perhaps I should go back and more carefully track, where's that 8 come from? Where's the 16 come from? Because if it stays simple, you could do this blob model thing, which is what I've been describing as like a medium level step mechanics question. And in some sense, I've just obfuscated that. And all of the fluid dynamics I'm doing is just kind of obfuscating that, bringing in some viscosity that doesn't really matter. So some things are true, right? Whatever shape this thing is, so whatever shape this thing is, mass is conserved. So the total amount of mass, you don't need to solve for the shape, you just know the total amount of mass. Yeah. How long does this take me? Oh, so this is... so this bit is the first bit of my thesis, which happened unusually quickly. We got the first bit up to... Where are we? Up to here or something. Oh look, there's a blob model. There you go, there's a blob model. I didn't try and draw it in 3D a moment ago. Keller, Joseph Keller, amazing. Fluid dynamicist, physicist, mathematician, everything. Blob. Blob, 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 blob. The snowplow was good, wasn't it? I should say snowplow more. I haven't said that before. So this took about 6 months. And then about 3 years of trying to do the opposite problem. 3 years of trying to do the problem where you have air on the outside, fluid on the inside, bit of viscosity, bit of inertia, bit of everything. Try and solve that. The other way round was, yeah, quite a bit harder. Hey, this is a good moment to go like, yeah, I did do this, didn't I? I'm pretty sure I colour matched. Pretty sure I colour matched that blue to be the same as that blue. Theme. Okay. Right, what are we doing? Oh, just now looking at my thesis. Okay, shall we switch? Was I right? I think I got the coefficients right. I might not have put the row in. 2 seconds while I go and see. For my own pride, we're going to look at the picture of the snowplow again and check if I put row downstairs. If not, we're going to do a minor correction. Where was the snowplow? Where was I? Ugh. I did put a row downstairs. Alright. No correction needed. Okay. Let's get rid of that for a second. I have an idea for content. Differential Galois theory. Oh, that sounds hard. Thanks for looking it up. I'm not sure I'm actually going to follow up on it, but yeah. Okay. So I had this idea for content. I was at the gym and I thought, what do I actually want to do this term? Like, what's a good thing that's kind of useful that I can do this term? What am I not doing? So I have a kind of idea. Lots of the biggest streamers I've seen, that they have some sort of beef. They have some sort of fight going on, or some sort of war with someone else. So I've decided that it'd be helpful if I had some beef, and I've picked Cambridge. So don't watch if you work at Cambridge. But my plan for the rest of this stream, is the following kind of incredible troll that I've thought of. Let me show you. Works like this. So that goes there. This goes there. Okay, hear me out. Hear me out. Here's the troll. Here's why this works as an incredible troll. I've been running something called the Matt Livestream for several years. The Matt Livestream is aiming to get people better at math questions. What if I did a step livestream? What would happen? Well, the idea would be that people would get better at doing step questions, and people would see some step questions and we'd all learn and grow and do better at step. There is a really funny outcome that might happen, which is this. Cambridge right now have made more offers than they have places on their maths course, by quite a large factor, I think. So lots of people have got Cambridge offers if they get the grades on step. So something really funny that could happen would be if everyone got full marks on step. If everyone gets full marks on step, then everyone goes to Cambridge, causing chaos. So let's hope that the Cambridge people, haven't bored by looking at my thesis for 40 minutes. They won't see this. But kind of behind the scenes, under the disguise of a chill math stream, we're going to do a bit of step. Also, this is personal, so we have this like funny outcome. Everyone passes step. That would be really funny. But we also have this kind of personal vendetta. Step 2010 was really hard. I haven't looked at step papers since 2010. 2010 kind of beat me. And I haven't looked at step papers since. So partly I'm doing this to see if I can get fighting again to do some step questions. We are doing step live stream until Cambridge tell me to stop. Oh, until Cambridge tell me to stop. Okay, let's see how long that takes. We've picked the perfect moment as well. We've been streaming since about September, and we've got quite a lot of like chill math streams on the YouTube channel. This is the perfect time to start just doing some step maths. You ready? Am I going to promote it? That'll be funny. 2010 was my year. It was tough. It was really tough. So much that I didn't want to look at these step questions afterwards. Okay, I think they'd pay me to do it because, or maybe work would pay. Maybe my work would pay me. Yeah. Anyway, right, good. Okay, so we're gonna start 2011. Welcome to the step stream. Everybody is permitted, by the way, to make one step joke. Total. Choose yours wisely. You can do exactly one. There's lots of angles you could go for, but you can do one step joke each. Yeah, one. Yeah, and you let me know if you're cashing it in at some point. Okay, right. So we're going to look at step questions. Here we go. So we're asked to sketch something like this, and it's got square roots in it. Classic thing that I need to make sure I get right is to make sure that I get these the right way around. So 1 minus x comes down and goes through 1. It looks like this. And 3 plus x square rooted. So when x is minus 3, it's going to be like that. So this thing is only going to be defined between minus 3 and 1. And I think it's going to look like... guess I should use blue, green, anyway. Between minus 3 and 1. And when this bit is 0, this thing is doing something, so it's going to be like 2 over here. And when x is 1, this bit's 0, but this bit is 2 again. And I guess it's going to be sharp, so steep at both ends, and come down like that. Okay, use your sketch to show there's only one real value of x that satisfies this thing is equal to x plus 1. And to do that, I suppose I'm going to need to label some points. So where are we? I said when x is 1, this thing is 0 and this thing is root 4, commonly known as 2. And then what do I do? So x plus 1, I'm going to look at, that goes through 1, 0, 1. Is it as simple as saying that it goes through 1, 1, 1, 2, sorry? Is it as simple as saying it goes through that point? So I use my sketch to show that. I'll say, well, I'll write out a sentence that says something like, well, this thing is bigger than 2 for x less than 1. And then after that, it doesn't exist because you can't take square roots of things that are negative. Whereas the blue line, x plus 1, goes through that point and then it doesn't. Let me just check. So if I put in 1, yeah, that works because square root of 4 is 2 and 1 plus 1 is 2. Welcome to the step stream. Some of the jokes carry over. That was me using. Anyway, good. Okay, graphically, number of real solutions that satisfy this. So this equation looks very similar to the one that I already had, but with 3 minus instead of 1 minus. I think I'm going to sketch that. Minus 3 and 3. And when I put in minus 3, it's like there's some like root 6 stuff going on in here for what the value is there. And then this 2 root 1 minus x stuff, that's something that comes down like this. What do I want to do here? A bit worried about having a second solution. Maybe I shouldn't be worried, maybe I should just go for it by not doing my sketch very carefully. Yeah, let a variable be 1 and see what happens. That's quite good. Yeah, I like that. Addition still works in step, we're doing it. Okay, so when x is 1, this thing is 0. I'm also trying to go fast, which is probably a mistake. Step, you get loads of time. Yeah, for example, what's this value up here? When x is 0, you get root 3 plus root 3. That's 2 root 3. Sanity check, is 2 root 3 bigger than root 6? Yes, because root 6 is root 2 root 3, and 2 root 3 is 2 root 3. 2 is bigger than root 2. Okay, so I've got this shape on the right, and I've got this thing on the left, which is going to be like a... I'm taking my time with this one. When I put in 0, it's going to be 2. 2 is down here. 2 is really low, isn't it, on this graph? Root 6 is huge. It's between 2 and 3. This thing's going to come up like this. So I think I should draw it like this. And the crossing's over here for some sort of value of negative x. I think I like that. So the green lines, this thing's decreasing, and the blue curve is probably, I've drawn it as an increasing function. I think it probably is, so there's only going to be one turning point over there. I think that's right. I haven't drawn this very, very good for this 2 times root 1 minus x. When x is 0, you get 2, because 2 times 1 is 2. It doesn't go through that point. It's still a bit low. Okay. And then it says solve this equation, which is something I enjoy a lot more than drawing pictures of curves. Because solving this equation, I've got some ideas, right? Maybe you could let me know in chat what you would do. I will pause for a second for that sort of thing to happen. While I start thinking about my picture on the right hand side. 10 seconds of thinking. Yeah, okay, that was enough thinking. I'm now happy with my picture. It's off the right hand side of the screen. I need to stop doing that. How do I stop doing that? I guess position everything, try to stay on the page. There we go. Try and stay on the page. There we go. Okay. Solving this equation. It's got lots of square roots in it, and I only know one way of getting rid of square roots, which is to do some squaring stuff. Right? 3 and minus 3. So I think I'm just going to try squaring everything. Squaring is a bit dangerous, of course. Maybe you know this, but you probably do know this. When you square, you introduce extra solutions. So, for example, I've squared, but I would get the same thing when I squared if there was a minus sign in the original equation. There's not, but if there was a minus sign, then I would still write down this thing after squaring it. That's dangerous. I need to remember that I'm solving the original equation. And on that. Yeah, imagine Ash was going to square it as well. Squaring it's gone quite well, I think, because, well, look, I've got the x and the minus x from squaring each of these terms have cancelled. Sadly, I do get this cross term with a 2 out the front that I forgot from multiplying these brackets together, multiplying these terms together. Did forget the 2, embarrassing. Not a great start to the current run of the Step live stream. Oh, I don't mind that too, actually, because now everything's even. So I think I'll probably divide. And this is going to catch me out, isn't it? Because this looks very negative, but my next move is probably going to be to square both sides again. And there's going to be a big trap here. I've got to be very careful about this whole sort of thing. Does that look like a quadratic I can solve? I'll have a go. I've probably messed up some numbers somewhere. Hey, look, Charlie learned a thing about negative signs. This is great. We're if nothing else, there's sort of secretly a plus minus here, which we've lost by squaring. We got to check. We can't remember which one. We can't remember which problem we're doing anymore. So we're going to go back and check. Sometimes you introduce a new problem, and the new problem didn't have any solutions anyway, so you get away with it. But sometimes you introduce a new problem with extra solutions. Okay, what are we doing? I was going to try and factorise this just really quickly and skillfully, but turns out that's the sort of thing that I've got worse at. Not seeing it. B squared minus 4ac. Yeah, I think I've made a mistake because I've got no solutions, right? Where's the 2 come from? Right, skills. Skills immediately launches step stream immediately screws up. Where does the 2 come from? Well, I'm squaring, right? So I should get 2 times AB, and then this thing really is 9 minus x squared because I can push the square roots together, I think. I've tried to subtract 6 from both sides. Rewind. Maybe it stays too low. Maybe it never solves. No, that'd be rubbish. If there's no solution, this would be a stupid question. Maybe I can't because I found a minus sign. 2160 is 176. Yeah, I don't love this. Let's just formula it then. Don't love it. We'll take it. Okay, formula it, but then check your answers. I want the negative one. I feel like I've made a mistake, so I'm going to move on. Yeah, disappointing. Should we Desmos it and see what's going on in Desmos? Let's try Desmosing it quickly. This is closure. Ooh. Don't get access to Desmos in the exam. Oh, it misses. Oh, I missed the factor of 2 this time. There we go. Okay, so it did not a bad picture. And then this number is horrible. That was pretty horrible. Yeah. What was the equation we had? It was this, wasn't it? Plus 4x minus 8? Yeah, nailed it. Okay, that's where the point is. Solve the quadratic. So you look, you get 2 solutions for the quadratic. You get this one, and you get that one. Ugh, that's not correct at all. Ooh, that is an interesting idea. Let's go and have a look at that. Neutrino. It's sort of an hour ahead, but also an hour behind. Time zones, eh? They're weird. Multiply by the difference. And then you've got the difference of 2 squares. That's going to simplify the right-hand side so much and make the left-hand side awful. Not doing it on the screen. We're moving on to the question 2. Okay, I'm disappointed that this doesn't have nice solutions. Maybe it's to stop me guessing. Anyway, right, question 2. Casually, solve Fermat's last theorem-ish. I mean, it's not going to be Fermat's last theorem, right? But it's kind of close. Fermat's last theorem is about x cubed plus y cubed equals z cubed. Okay, I'm not going to write down my cubes. That's the hard one. I don't enjoy writing down cubes. I've changed my mind and I'm writing them down. 5 is 125 and then 4, 64. Why am I writing down these cubes? What is this question? 8, where did I get down to? 5, 4, 3, 2, 1. Why did I do them backwards? A perfect square is what people sometimes say to mean square number. After someone's been like, hey, technically 7 is square because it's the square of root 7. So usually mathematicians have that discussion one time. They say, I mean a square number, and someone says, what about 7? That's the square of something. And you say, okay, a perfect square number. To me, a whole number. That's a square of a whole number. Right, okay. Is a perfect square number. Okay. What are we doing? X and y. X is less than y, and they satisfy this equation, so that stops me switching around x and y. In the case x plus y equals k, I guess that is a case, but that's a bit weird. Why have they said that? Anyway, whatever. X plus y is k. So first instinct is to plug in x plus y over here for that k. And hang on a minute, I think I know a fact that this factorizes with an x plus y. Maybe that is where I'm going. But hang on, yeah, I want z cubed. Yeah, I want z cubed, so I want to divide by this k. So I'm going to factorize this left-hand side. Factorize the left-hand side, and then the remaining quadratic junk I will try and turn into this quadratic junk. That's my game plan. I want the step stream to be mostly game plan and identifying what we're supposed to do, rather than actually me doing too much calculation on the stream, because I'm liable to get this sort of thing wrong, especially while I'm talking at the same time. This question is a little bit more algebraically involved than math questions, so I don't know, good chance that, so this is verses. I would never write verses in an actual exam, but there we go. I have this thing. We are told they're equal. A bit more algebraically involved to finish that thought, so it's unlikely that I can talk and do maths at the same time, which is why I want the stream to focus on getting plans about what we're doing rather than actually doing it. Case in point, I was just saying 3 things at the same time while also writing. Don't do this at home. Yes, right, okay. So z cubed is equal to x squared minus xy plus y squared. Now, I can see the thing I'm aiming for has just got k's and x's in, and the thing I've got has got y's in. So I would like to eliminate the y's. If you're playing along at home, you can see how I'm going to eliminate y in favour of x's and k's, right? I'm going to use this again. Always back to the facts that they've given me. I mean, I could use this, but it's got loads of z's and k's, and also more z's. I guess I'd be hoping the z's work themselves out again, but I'm currently happy with where I've got the z cubed. I've got z cubed on the left. If you would like to stop writing down the letter z, so I think I really am going to go back to this and just plug in k minus x. I might not even, so 4 k minus x plus k minus x squared. I might not even actually multiply that out. I'll just have a quick think about it. What am I going to get? X squared here, and x squared there, and x squared from the last one. That's 3x squared. I'm definitely getting a k squared from this term over here, and then a whole bunch of cross terms. Negative kx here, negative 2kx over here. So yeah, I think in the middle. That's going to work out fine. Okay, so I'm down to this deduce. And that's asking me to multiply by 4. Take off a k squared and divide by 3, which is k squared take away 4kx plus 4x squared. Oh, this is rubbish. This is just k minus 2x squared. Okay, it's a perfect square because it's exactly k minus 2x all squared. That's, I guess, completing the square or doing some quadratic stuff, or just recognising this pattern of 4s and minus signs. I've seen this before. It's basically the sort of thing I was just multiplying out over here. Okay. So in this particular case, where the sum of 2 cubes is k times z cubed, and also that factor k was the sum of the numbers, then it would be the case that 4z cubed minus k squared over 3 would be a perfect square. Sometimes I try and keep track of what's going on, and that didn't really feel like I knew what was going on, but you've got to try something, haven't you? 1/4 k squared z cubed. So z cubed is between 1/4 k squared and k squared. Try to put it into words. Z cubed is between. There's an equal sign on that one and not on that one, I have noticed, but I'm going to try and think about z cubed first. Right, so can I see why z cubed is bigger than 1/4 k squared? No. Can I see why it's smaller than k squared? Yes. Because this is... No. This is not z cubed, is it? This is this mess over here. I was going to say this is smaller than k squared, because that was the thing I'd just written down, but in fact this is not z cubed anymore. Right, let's have a quick think. So is z cubed, the question of like, is z cubed smaller than k squared is precisely the question of is minus 3kx plus 3x squared negative? To which the answer is presumably yes, because that's what we're trying to do. But let's factorise it a little bit. Is this negative? And the answer to that's got to be yes, right? 3 is positive, x is positive, so it's not going well. X take away k, well, k is x plus y. So this thing is negative y. I assume these numbers are positive numbers. Oh, good news, they are positive. Phew. So this thing overall is going to be negative. So yes. I would then reverse it. Sometimes I do this thing to say, here's what I want to prove, and I go and work out what that's equivalent to. And then I say, brilliant, minus 3xy is negative. So I'm going to then explain that by writing it out the other way around. Okay, we're also going to prove that z cubed is bigger than 1/4 k squared. It's quite tempting to choose the same sort of strategy. The question of is z cubed bigger than 1/4 k squared? I've now decided basically that this is unrelated to the previous thing. That seems stupid. Yep, as I said that forced me to look back at it again. There's a 4 in there. Isn't that just... Yeah, neutrino, do it. Hit it. I've set it up. Yeah, you can knock it out of the park. Go on. I've teed you up. Go. Carry on. There's a factor of 4. I've just said I think it's unrelated, but wait. It's 4 z cubed. It's a perfect square. What do we know about perfect squares? Perfect squares are positive. Yeah, there you go. Excellent work, neutrino. Is perfect square, or that over 3 or something is perfect square. So it's greater than or equal to 0. And then you rearrange that, and you get the z cubed is bigger than k squared over 4. Oh, there was a point to that. That's good. I like it when I didn't really know what this was for. Maybe the answer to what's this for is just to prove that, and now we're done. I'm going to stop thinking about it. Oh no, I have to do more thinking. This is good. I like it when the pieces link together. Good. Use these results to find a solution of star when k is 20. Oh wow, okay. So what do we have? For the particular case k is 20, I'm going to think that we would want x cubed plus y cubed to be 20z cubed. And we're like in the case, which I don't really love that phrase, but never mind. We're in the case that the sum of the numbers is also coincidentally 20. It seems weird. And we've just proved, great effort, that z cubed is somewhere between 400 and, what is this, 400 divided by 4? 100. My tea is a bit cold. I'll do it at the end of question 2. Ah, there we go, there's motivation. 10 past 3. Now I see why they got me to write out those cubes. Wait, no, I've circled not enough of them. There's a bunch of them. Oh no, they got me to write out these cubes. So it could be 5 cubed, or it could be 6 cubed, or 7 cubed. Those are the cubes in between 100 and 400. We're going to check them. Is it work to check them? Slightly, I guess. Because I'm going to have to think about... Oh, I know some cubes, right? So checking if my cubes actually sum up to the right thing. Is that all right? One of them... Can I get around this? There's kind of 3 possibilities, and I'm sort of too lazy to check 3 possibilities. Maybe I'll leave that for the tea break or something. Because I'm going to multiply those, what, by 20? So I'm looking for 2 numbers that sum to 20 and whose cubes sum to maybe 2,500. Doesn't seem like the sort of thing I can actually do, right? Oh, I like that suggestion to look at the last digits. 216 doubles to 432. 343 doubles to 686. Oh, yeah, last digits is presumably the way to do this. Oh, I can't see because I've gone off the screen. Yeah, right. Okay, I've got to fix that. I'm doing the thing where my The thing you're looking at is 4-3. The thing I'm working on is 16-10 or something. Screens. Thanks, Charlie. I'll keep one eye on chat. That'll be alright. If I click here, then it kind of is good. So as long as I remember to keep clicking. And the numbers are supposed to sum to 20. So my first guess is to do like 19. Because maybe there's a chance that that's about 2,500. Maybe? This feels silly. What am I doing? Am I really going to do this? Yeah, numbers that sum to 20. Last digits is a good suggestion. Okay, I think I'm just going to work out 19 cubed. Just start there, see if that does it. Do I know 19 squared? A bit. I hope this does it. This is not going to do it. This is disaster, isn't it? Isn't this way too much work? No, bingo, got it in one. Okay, so 19 cubed plus 1 cubed is 6860, which is 20 times the third one. 20 times 7 cubed, I think. Don't get a calculator in step either, do you? Okay. My ability to multiply numbers together sometimes surprises me. I was listening to a teacher talking about how they use what's 7 cubed as a good way to think about what's going on good way to find out what's going on in people's minds when they do mathematics, because there are many ways that you might work out 7 cubed. You might just know that 343 is the answer. You might work it out in steps. You might have some clever way to do 49 times 7. You might not be doing 49 times 7 at all. It's a really interesting way to think about it. Sadly for me, I just know that 7 cubed is 343, so I don't get to do any interesting think about how you would work it out maybe. 1 cubed and 19 cubed, I realise now that looks like I pulled it out of the blue. That was me slowly resigning myself to the idea that I was going to check things from, x is less than y, so I was going to check starting at 1 and go up to 10. There's not that many pairs, right? There's 10 of them. So adding them up, right? Just try. You've got to start somewhere. And I foolishly thought that 19 cubed was going to be about that big, and I got sad when it was larger, and then it was much larger, so I was done. Okay, right. By considering the case x plus y equals z squared, that's mad. That's just crazy. Like 2 solutions when when k is 19. Right, okay. If I do this, then I can go have a cup of tea. 10 cases is too many. If it was the case that 10 cubed plus 10 cubes was the answer, then I'd, this stream would be quite long. Right, 2 solutions when k is 19. So I sort of see what they're doing with this x plus y being z squared, because that's also a factor of the right-hand side. So if it's the case that x squared plus... Hey! Thanks for that. What was that? That was tea time. I'll redeem that in a second. Tea time applies to all of us. One is not. One is not as large as 10. Welcome to the step stream. What are we doing? What are we doing? I don't really want to plug this in to that quadratic. Oh, k is 19. So maybe... what am I doing? X plus y is z squared. And the sum of those things is 19z. Okay, so that's the challenge we're going to solve. I've got some ideas. I might try squaring that second thing. That's stupid. Don't do that. Don't square the second thing. It gives me lots of the same things in the line above, but also z to the 4. Yeah, I might just do that. That's not too bad, right? Let me know in chat what you would do with these two equations that you want to try and simplify. Those are the two equations we've got. Those are the two equations we've got there. We're looking for integers. Yeah, I think I'm going to square and do some difference. So like xy is equal to z to the 4 minus 19z, which is z cubed, z minus 19. So I've only got a few possibilities. My z's got to be at least 19. Seems a bit unlikely. Wait, hang on. X plus y is z squared. So then my x and y are going to be huge. This doesn't sound right. X plus y is z squared. K is 19. 19 times a third cube. Am I right that it's kz? Have I killed off the factor of x plus... Ah, there's a minus sign over here. Minus sign from all this quadratic junk. I copied it out wrong. What does that mean? Means there's a 3. Hello, melt like butter. Thanks for the follow. We're doing some step. We're going to subtract that, but it's got a minus sign in. Yeah, so this says, I think this is legit and says that z's got to be large. Hi, welcome to chat. You came here to see maths? We're doing some maths. We're trying to solve, it's not quite Fermat's last theorem. It's Fermat's last theorem with a factor in the right hand side. Is it x cubed plus y cubed over here? Oh, and I'm zooming everywhere. X cubed plus y cubed on the left, and it's got kz cubed on the right. And we're considering the special case where x plus y also sum to z squared. And k is 19. This is quite a special case of something that's not quite Fermat's last theorem. We are trying to do that by writing down those as simultaneous equations. And x plus y is secretly a factor of x cubed plus y cubed. So I've pulled that out and divided by z squared. And I've remembered that k is 19. But that's kind of all I've done so far. You want to multiply them? Why won't they just give me back where I started? Yeah. Multiply them. So it's going to be positive, so that's going to be huge, right? Let's just quick check. What if 19? What if k is... What if z is 20? That's not a multiple of 3. What if z is 21? Well, then I get 21 cubed times 2 on the right hand side. 3xy on the left, and I flipped them. So then I've got the product of the numbers is huge. The sum of the numbers is 361, which is, or 441. So then I'd be solving like, in this, if this is the case that z is 21, which doesn't seem impossible, then I'd be solving something like this, which is quite a lot. Quite a lot indeed. Yeah, not sure about this. Pull out a factor of 21. So I've got this stuff over here, and I'm trying z is 21, just because it gives me a factor of 3, and it gives me a nice small number on the right hand side. Well, I say nice, small enough. And my next guess is to just sort of try stuff that's, try stuff that's multiples of, try stuff that's multiples of 21. If I could find two numbers that sum to 21 and multiply to 14. I can't think of any of those though. Yeah, okay, not happy with this. Back up, back up. Considering case x plus y is z squared. Considering case x plus y is z squared, I've got this term on the left hand side. That's a factor of the left hand side. I definitely want to use that. Kz on the right. Yeah, scroll to get the question back on the screen. There you go. It's gone a bit messy, hasn't it? Let's tidy this up a bit. It's the classic writing all over the question. Let's lose these cubes. We might need them in a bit, but whatever. I tend to underline absolutely everything. So last time we proved lots of inequalities and things, which seemed clever. Do we want to try and do something like that in this case? Well, I haven't got down to an expression for z cubed, have I? My z cubed expression would have to be something like... Yeah, I cancel the k. Didn't cancel the k this time, I cancelled some z squareds. Okay, let's talk about it. And then I go for a cup of tea. As the motivating force. Solve it, have a cup of tea. X plus y z squared. I really want to pull out the factor of x plus y. X squared minus xy plus y squared. What you're not getting here is you're not getting top tier math solution. I haven't looked at the question in advance, as I said. I haven't looked at the step questions since 2010. Yeah, get an expression for 3xy. I do another expression for 3xy. I think that's the one I've got, isn't it? X plus y squared, take away 2xy. Oh, x squared plus y squared. Yeah. I think I'm going to end up with this z to the 4 minus 19z thing. It's a bit awkward. I'm an idiot. A big dum-dum. Should we zoom in on the big idiot moment? What is this? What is this? What have I done? Why have I done that? I is big idiot. Okay, when you're factorising, it's important not to pull out factors that aren't in both terms. That's what we're learning. Oh dear. Right, cool. That makes all the numbers much smaller, which again makes me think that I should just try and work with this, you know? Work with it. Move against it. Try small values of z, see what happens. The alternative, of course, is to take, I've got an x plus y, I've got a 3xy. You can solve stuff like that. Solve x and solve it in terms of z. My calculations down here were all nuts because I had too many z's in there. Should we try some small values? So someone asked as well how I got an equation or something. Melt Butter says, how did you get z cubed is x squared minus xy plus y squared? And I have kz being that. My original equation has this x cubed plus y cubed, and I've used the fantastic fact that x cubed plus y cubed is equal to x plus y times x squared, polynomial division, let's go, x cubed minus... Neutrinos also factorise the same line wrong. Okay, x squared y, so I subtract an xy to take off the x squared y, but that gives me a minus xy squared, so I add on y squared, and then brilliantly I can stop. Oh, right, so that's the factorisation. Yeah. So what I've done is I've taken the first pink circled line, this thing over here, and I'm supposing as well that x plus y, this thing over here, is z squared. So I've got z squared times this quadratic is equal to kz cubed. So I've tried to just divide both sides by z squared and write down horrible quadratic, and over here, kz. And then I remembered that k is 19, so I put 19 instead. It's possible I've screwed up in multiple ways along the way there, but I think I'm all right. Okay, so I think that means z cube's got to be at least 19, which is not nothing. Should we check 3? So what happens if z is 3? If z is 3, then I get something like xy as I'm skipping lines again, which is dangerous. I get something like xy is 8 and x plus y is 9. It'd be lovely if I could just solve some of these things, right? I wait, I can solve that. I can solve that. Yeah, if z is 3, checking small values of z. Hooray! Z cubed minus 19 has got to be positive because xy is positive. So I've tried the smallest thing that I could think of. Not 1, not 2, 3. 3 cubed is 27. Take off the 19 really is 8. The 3 here cancels, so I get xy is 8. X plus y is 9. I can solve those. 1 and 8. I've got a 1 solution again. Okay, so I think that 1 cubed plus 8 cubed is 28. So 19 is no, 8 cubed is 64 plus 1 is 65. 65 is 13 times 5. Not multiple 19. What am I going to put over here? It's not 19. What am I doing? What is going on? This is maybe a good example of how I don't know what I'm doing. What on earth is going on? What have I got? I've got x plus y being 8 cubed is not 64. Thank you, gang. What is 8 cubed? I've erased all of the cubes. It's 256. It's 257 versus. Is this actually true then? Is 27 times 19 really this? No. Still not right. Is it 512? How am I? Oh, stacking up so many L's in quick succession. I have no idea what's going on. That really is 27 times 19, isn't it? It is. It is, isn't it? Huh. Cool. There's another solution, but it's 8, 1, and they told me that x is less than y. Okay. It does. Okay, so we worked something out. Good. We've got 1 solution. They told me to do 2 solutions, I think. Find 2 solutions. If I find a second solution, can we use the last part? With all of these inequalities and things. What made you think 3 would work? I'm very lazy. I thought that this would be... I need this to be a positive number because xy is positive. And if I want this to be positive, I've got to make z cubed large. I'm not very good at remembering my cube numbers, but the smallest one that is bigger than 19 is 3 cubed. And then I checked what would happen. I'm going to try 4 next. So the equations that I'm solving, I don't know why I've done this. I don't know why I've done it like this, but instead of solving the pair that were nice and easy to get up the top here, with the 19z equal to this quadratic and the z squared being this one, I've decided to do this mad kind of rearranging to get an equation for 3xy. Maybe I regret that, but only a little bit. So I think maybe this is going to be... there's a chance this is not a multiple of 3, which would be nice. Not nice, but... No, that's 45, isn't it? My mental maths is nowhere near as good as it should be. So now I'm looking at 3xy as this. 445s are 180, so xy would be 60. And x plus y, meanwhile, would be 16 or something. That doesn't look very sensible. Okay, so can I think of any solutions to that? I mean, there's a quadratic way to solve these. I'm just being lazy. Ten and 6. Okay, so I think this is true as well. And I can do the left-hand side. It's this. So the thing I need to check is that this thing, 4 cubed is 64, really works. 20 64s would be 100 and... Take away this, take away 64, really does work. 20, yeah, 10 and 6. Thank you, Moto Butter. 10 and 6. I'm supposed to list x is supposed to be less than y or something, so I'm supposed to call it 6 and 10. There we go, good. Okay, we've got a second solution. Who knows if they keep coming, but did it. Woohoo! 2-step questions done in like 45 minutes or something. although I'm not really sure I finished this one. There's a quadratic. Right, okay. I'm going to quickly make a cup of tea. If you would like to take a break and make a cup of tea, then go for it. When we come back, we are maybe going to do question 3 or maybe question 4, or maybe one of the other ones. That's in 2 minutes when I'm back from this. Back very soon with a cup of tea. Woohoo! In chat, yes, 1280 take 64. Yeah, cool. Woo! We're back. Wonder if anybody else did go make a hot drink. I've gone for coffee because it's faster. Twitch is telling me that I'm still live. We're still here. It's a step stream. Thank you, Mary. Thanks for redeeming channel points for this sort of thing. Have a little walk around. Yeah, stretch your legs. If you've been looking at a stream for the last hour and a half, we'll have to look somewhere else. Like Bella says, this gives you joy, doesn't it? I'm not sure if they're talking to me because I was out making a cup of tea, but yeah, that little endorphin rush, it balances out. The times when I do something stupid is, for me, balanced out by the times where, I don't know, you're plugging through and it just works. You get a pair of equations, you're just like, yep, I can solve that. Or the kind of understanding bit, where maybe a better example is the moment where I was talking to Neutrino in chat about this. We went from here, but didn't really know why we'd proved it was a perfect square, to here being asked to do something random and spotting the link between those things, that, aha, this thing involving the 4 is something like that. Right, which question next? Let's do a quick chat vote, I think. I would like to see question 6 because I thought about it before the stream. I got slightly nerd sniped and started just trying to do the questions before it went live. I had to load them in. Let's have a quick look and then we'll do a poll. So, what can we see? Increasing functions. Yeah, show it's fine. Increasing. Show that this looks easy. I mean, it looks unscary, but also not that bad. Show by considering this that that looks hard, but also, neat. Tan times arctan bigger than x squared. I would like to know that. This looks like classic sine 18 degree stuff. Given that, extra things. Is that oh no for oh no for increasing functions? Vectors. I like a good vector question. What's actually going on here? We've got a triangle OAB. They're not collinear. And C is the reflection of B in the line through O and A. Show that C can be written in this form. Okay, fine. D is the reflection of sine. It's a reflection of C in the line through O and B. this goes like this, and then this goes over here. So that D can be written in this form, determining mu. Given that A, B, and D are collinear, they do not look collinear in my picture. A, B, and D are collinear. Find the relationship between lambda and mu. Sounds like classic vector stuff. Tell me the cosine. Okay. In the case where you're told a number, find out basically where stuff is. Cosine makes me think dot product. Relative positions of A, B, and D sounds hard, but they're collinear at that point, so it'll just be that on a line separated by some amount. Okay, and then there's this question with some integrals in. Hence find sine to the 4 over cos to the 8. Sounds good. And this is in my favourite format of a step question, where you do something mad, and then part 2, they do something hard and unusual. Then the second part of the question, they give you a particular example of that, and then the last part, they just tell you to find it, a different one, without telling you they take away the stabilizer wheels, they take away the guardrails, they take stuff away. Okay, we'll do one of these next. I think we'll do a quick poll. Manage poll, new poll. We've got Q3, Q4, Q5, Q6. Have I got enough viewers to do a poll? Not sure. I've got at least some. 6 says Mary. I've actually set up a votey thing, and I think because the settings have carried over, I think you can also vote with points. Quick review while that poll's running. There's a question about increasing functions, where the punchline should show that tan arctan is bigger than x squared. There's a question about sine 18 degrees and root 5s and things, where you show that solving this equation at the end looks really tricky. There's a question about vectors, where I doodled a little picture over here. And there's a question about integration, adding in f's and f to the n. If you can't choose, then don't worry, a random thing will happen. Poll is messed up. The one you want is winning, so I'll die on that, and everything will be okay. Yep, the one you wanted won. Okay. There we go. Question 6-1. Oh, that's nice of you, chat. It's also the one that I said I wanted you to pick. I love democracy. Okay. So I had a quick look at this before, because it's the sort where I get to reuse a thing. It does look fun. Look at all this sec squared, sec plus tan to the 6. Okay, given a function f, let I be this integral. Zoom slightly, but try not to get too carried away. I've got to not go off this page. Okay. Show that if f satisfies second derivative is kff prime for some constant k, then star can be integrated to obtain an expression for I in terms of those things. So, why do people solve insanely difficult problems? Well, sometimes because they want to know the answers in order to improve the world. Sometimes because they want to know the answers to push human understanding of things that we can't do. Sometimes because someone else has said it and it's a kind of challenge. Just really like the challenge personally at the moment. This is not pushing human understanding because somebody else just wrote this question. Sometimes money. I'm probably going to integrate by parts, chat. I'm going to integrate by parts because I can see something that I would really like to differentiate to get this f prime prime involved, and something that I don't mind integrating. Yeah, this thing is the derivative of f to the n plus 1, right? So I guess this thing, can I do it by parts? Yeah, I can do it by parts. I was worried about that. I was worried about something stupid. I was worried about the lack of limits. But integrating without limits is just, free your mind. There we go. Good. Yeah, when I differentiate that, I will get f to the n, and n plus 1 will cancel, but also I'll get an f prime out because of the chain rule. These are my parts. If you haven't seen integration by parts yet, don't worry, there's this way to change an integral into a different integral. I am hoping that this gives me a nicer integral to do. F to the n plus 1 divided by n plus 1. I really hope n's not minus 1. Oh good, n is a positive integer. I like this way of like, I didn't read that the first time round. I probably should have. I didn't read it. It didn't go in anyway, but now I really want it to be true, and I look back and that sort of condition is stored near the top of the question. Okay. So if you haven't seen integration by parts before, it's a way to convert one integral into a different related integral. This is ruled, and it comes from the product rule. It's not super difficult to learn the first time round. Right, what am I doing? If f satisfies this, I'm probably going to use that fact, aren't I? Yeah, I'm going to use it now. So I'm going to copy this out. There is going to be a factor of k, a factor of 1 over n plus 1, and then in here there's going to be f prime f to the n plus 2 dx. Because I'm using the fact that this thing has got an f and there's secretly another f prime in there as well. Yeah, well, I don't know. It's just, this question is not good for convincing people integration by parts is a good idea, right? Because it's just converting one. Why do we want to do this integral? So why would we have this relationship into the thing? Bringing it all together. Right. Okay. I can do that one as well. That sounds like showing off. K over n plus 1. Because again, when I see this, I recognise that this is something that's been differentiated. You know, it's not quite f to the n plus 3 differentiated. I've got to divide by that n plus 3. Yeah. What are we talking about? We're talking about tan in chat. Why do we have to do it generally? Yeah, so I'm still up here. In a moment, f is going to turn into tan, and then we'll be good. So I suppose there's two things I'm supposed to check. Part one, I've got now this expression, I should add a constant. Yeah, I should add a constant. This is not in terms of f prime, k, and n, excuse me. It's actually impossible to determine exactly what this should be in terms of just f prime, k, and n, because I've got a constant that's independent of all of those things. Right. Here we go. Yeah, step questions are sometimes sneaky in that they have sometimes instructions for you to do stuff before you get to part one, and maybe in between the parts, which and I guess this is sort of part of the part, but so many extra stuff. There's a lot of F's. Okay, so verifying in the case f is tan, I should probably check if f is tan. I should probably check f prime prime is kf f prime. I should probably check that. This will be a disaster if not. Can I remember how to differentiate sec? Sort of. Oh, that's been a little while. Differentiating sec is not on Matt, so I don't have to do it very often. What have I got then? F prime prime is exactly 2 times f prime times f. Oh, so that's all right then. Cool, okay. So this is an example where I'm now, because this thing is true when f is tan, this thing, I'm hoping that I can now make it look like this at the top. I mean, if I can make that look like the thing at the top, then I'm in business. What have I got then? Can I see any sec squared? So is it f prime would be sec to the 4, and then this would be multiplied by sine to the 4x over a further cos to the 4x down here, which luckily is exactly tan to the 4. So I think this is just n equals 4. So n equals 4, k equals 2 from the relationship that f prime prime does. And yeah, I haven't got my constants and stuff. But I should be able to just write this down, right? It's not going to be very fun. It's going to be like this, isn't it? So I'm now going to write down my answer as being, well, no, maybe I'll leave this as homework or something, but it's going to be like sec squared tan to the n plus 1, tan to the 5 divided by 5 minus 2 over 5 tan to the 8 over tan to the 7 because n plus 3 divided by 7 plus a constant. Okay, that doesn't look true at all, but that's what the formula that we've now got has given me. Amazing. I don't consider that to be the fun part of the question. I think the fun part of the question is, I'm going to erase that because I think it might be false. The fun part of the question is deciding what f is in that case, in this last case. So let's ignore all of my work. I'll just zoom in on this question here. There we go. So in the previous part, we used tan. They told us to. And we checked what would happen, that we'd get an f prime, which is sec squared, and then some more stuff, which luckily really was tan to the n. This stuff in the brackets here is tan to the 4. In this case, I'm not really sure what I want to do. I can't do tan again because this is not, well, it's not sec to the 4 times tan to the n for any value of n. Oh no, there's maybe a way where I multiply out the sec plus tan to the power of 6, multiply it out to 7 different terms, and do each of them one at a time. Not keen. So has chat got any other suggestions? There's a little bit of guesswork here to have an idea for f, and then we'd check whether or not it actually works, so that we can find the value of k, and also check that it works for our integrand. Guesswork, go! Neutrino, quickest off the blocks there with a guess. Sec plus tan. Here's what I have to do to check whether that works. Love it if I could just say yes or no. Here's what I have to do to check. I have to check that this thing really is f prime squared times f to the n for the f that Neutrino said in chat, and I have to check that the second derivative of f really is k times f prime. Oh, I missed the cricket chat. Missed the cricket chat and the idea of highlighting things in bold or underlining stuff. Neutrino's done both of those things and it checks out, so I think I'm just going to accept that. Okay, so apparently if you put in this f, what's going on with the sec squared then? Maybe it's nice. Let's try and do that. So I don't really care what the answer actually is, I just want to make sure I can make this work. We've got some expression at this stage. I keep zooming in slightly too much, there you go. So if f is sec plus tan, then f prime is, so when you hit sec you get sec tan, and when you hit tan you get sec squared. If you do two derivatives, then you get, my goodness. Yeah, that's the sort of thing I should write down, isn't it? Which involves an f. Like this. Here we go. So then the second derivative, I'll get sec tan f plus differentiate the other one, sec tan f prime, which is, and then that f prime over there is sec squared f using the previous line, sec tan f plus sec squared f, but that's exactly sec plus tan f. I think I've messed up just a little bit, but I think I've messed up. Yeah, I have messed up. This sec f is an f prime. I've not messed up. This is f prime times f. So this all worked out really nicely. K is 1. Oh no, Neutrino likes step now. This question's good. And also, the thing inside here, so sec plus tan, have we got an f prime in there? Yeah, we do. So then this is clearly this sec squared f to the 6, I want an f prime squared, so I'm going to steal, because f prime is sec f, I'm going to steal a couple of f's for my sec x f prime. Steal a couple of those, and I'll leave the other 4 over there. And then I've got exactly f prime. Oh, I've got exactly f prime squared, and I've got 4 f's over here, so n is 4 again. Write down the result. It's going to be a mess, but just write it down, I guess. So the cleverness here is choosing f of x to be something in the question, and avoid the trap of choosing the same f again. Good, yeah, melt like butter had the correct factorization. That was really helpful. The factorization of this derivative, which I guess you might have seen if you've seen the integral of sec. So this one is the kind of maddest one in the formula booklet, I think. If you want to integrate this, the solution to how you might integrate this, which is sort of silly, is to multiply top and bottom by sec plus tan. Top and bottom of this fraction, which is just daft. How would anyone think of that? Because tan differentiates to sec squared and sec differentiates to sec tan. So this is log of sec plus tan. This is nuts. But it's in the formula booklet. So it's the thing that people might have seen in the formula booklet, and they might have seen that reasoning for why it works. And if you've done that, if you've been like inquisitive and you've messed around with it and been like, well, why does it work? Shall I try differentiating this? And then you find out what the derivative of sec plus tan is. It's exactly sec times sec plus tan. And then you're more equipped because then you see this and you think, aha, I know how to differentiate that. Is a good result. I'm losing track a little bit of how formula booklets work these days. Possibly it was in my formula booklet and it's no longer in the formula booklet. Okay, this one was a bit longer, wasn't it? What came second in the poll? Can I look at the poll results? I can look at the poll results. Oh, I have to go over here. There's a single vote for question 4. There's kind of polygons. I've got about 10 minutes on the clock. Let's see if we can do some. Let's see if we can do the ideas of this. Oh, it's not in AQA, but it is in Edexcel. Good stuff. Okay, so this maybe means that AQA people have just learnt the integral of sec. Okay, yeah, vote for question 4. Okay, here we are. Okay, starts off pretty standard. I think, I say standard, but you know, do your best. What are we doing here? What's our strategy for solving that equation? I suppose it's probably something like, so cos is like, I probably want to write that in terms of a sine, right? And then these things might agree. You might have the case that 90 degrees minus theta equals 4 theta, or you might have 90 degrees minus theta is equal to 4 theta plus 360, or plus 720, or so on. So you get these other solutions. And you might even have the case, I don't think this works, but you might have the kind of 90 minus. So there's lots of things to solve. Sines being equal is probably the way I would do that. And there's a hence show, because I think you can also do something else where you get the result exactly. Let's think about how we would do that. It's going to be something about, I could use the fact that it's sine 4 theta. So go for sine 2 theta cos 2 theta using the double angle formula, which is then the double angle formula. I don't love it. Is this nice? I think I might have used something a bit like this as a math question at one point. So it's a little bit embarrassing that I'm floundering briefly with it. Yeah, and then there's a quadrate. There's going to be a thing out here, isn't there? There's going to be a thing down here somewhere. Cos 2 theta I'm going to write as 1 minus 2 sine squared theta. And this is 4 sine theta. And I'm going to solve that as a cubic, so I'm not very optimistic. Are there any obvious solutions? No. Yeah, that, melt like butter, that thing. Are there any obvious solutions that I'm missing? Neutrinos come out of the woodwork and said they've done this paper, they've done this question. Yeah, that's how I did it. Oh. I say out of the woodwork because I think before I was under the impression this was, well, it's fresh for me. What am I doing? What am I doing? I can't solve that cubic. What am I playing at? Yeah, well, okay, cool. I love trying to work out whether people are doing things live or not. It kind of really surprises me, the idea that I'm sat at home doing maths and maybe other people around the world are also sat at home doing maths. We're doing step next week? Yeah, maybe. I'll do a bit. Do you want that? I'm having fun. I'm having, I think, more fun than sort of vaguely wobbling through other sorts of maths. And Cambridge haven't told me to stop yet, so they've had an hour. Okay, yeah, this is what we're doing now. We'll see. I'm not going to run out of these. What am I doing? How am I going to solve for sine 18 degrees? Because that's one of the solutions, right? 90 divided by 5 is 18. So it's this thing. Whoop, this thing gives me 18 degrees. Am I being silly? No, I think I'm good. I just can't solve it. Why would this have nice solutions? Where's the other one? Where's the other one? Why are there only 3 solutions to that? Why would there only be 3 solutions? Warwick's doing a step thing. Everyone who isn't Cambridge live streaming step. What is step? Step's an exam thing. Oh yeah, can we do the Warwick one? Can we raid them on Twitch? Everyone quick. How do we raid Warwick? Live streams. Weekly 2-hour live step thing. Sounds really good. Maybe I won't do the step stream. I'll just let Warwick do it. Melt like butter in case it's helpful. This is a maths exam that's used for some UK universities. I had to do it when I was a teenager. So this is the fight back. Now I'm using it as content. I've stopped. Maybe I should just not stop, right? Can't solve a cubic. Yeah. Those offer holders for year 13. Charlie's going to learn so much maths off this. He's going to learn all the year 13 integration by parts and stuff. Really flummoxed myself, and I've only got 10 minutes on the clock. The clock's paused. Alright, there's the other one. I mean, it's silly, but there's the other solution. I thought there should probably be 4. well, let's just try and solve it and see what happens. Maybe I'm trying to just overthinking things. So I get an 8, I'll move it on the right hand side. I'll get minus 4x, not plus 1. Am I overthinking it? Is x is 1/2 a solution? No. So I'm writing out x as sine theta to save writing. So 4x minus 8x, but I'll chuck them over on the other side. Yeah, why am I so stuck on this? Maths in year 12, it's quite nice in a way. It's sort of annoying that you don't see complex numbers until ages, but you see, kind of self-contained course. Other content. One half is a solution. One half was a solution already. That's annoying. I think my mental maths is the main thing that's holding me back here. Maybe not the main thing, but he says factorising a quadratic wrong. What on earth am I doing? What on earth am I doing? Can we see the question? Yeah, let's have a look at the question. I spent ages, so I had a cubic in terms of sine theta, and I froze for ages without writing it down. And then I wrote it down, and I started looking for obvious solutions, like x is 1/2, 1, take away 2, plus 1. But then it doesn't, no? Yeah, something like that. It's something like that, though. That'll be something. It's something like that. Yeah, it's something like that. I'm quite keen to plug in 1/2 because that would give me 1. And 1 plus 1 is 2. Welcome to the step stream. Okay, let's try again. Let's try pulling out a factor of 1/2 again. But this time I'm going to mega concentrate. Minus 4x squared. So I need to add on 4. So I'll get my 4x squared back. But that's going to subtract 2x from me. And I'm going to subtract 2. It's going to give me 0. These things are not going to be whole numbers. These things are going to be horrible things. One of the nerve-wracking things is the way that step switches so easily between whole numbers and real numbers, and just doing all the things all at once. Okay, so then I'm going to solve this quadratic this time. Get minus 2. I'll do the jazzy thing. Minus 1 b squared minus ac is 5. I might have done that too fast. Something like that, which is kind of what I wanted. Why is there a divide by 4? Ah, well, can't win them all. Divided by a, right? Divided by a. And I probably want the one that is, well, minus sign would give me something very negative, and I want the one that's actually between minus 1 and 1, please. Oh, which is the thing in the question. Great, okay, that took me way too long. Notes for myself. Sometimes I'm just sort of frustrated with myself when I feel like I could have done something faster. For me here, I'd had the right idea. I'd used the cos 2 theta factor. We're doing it great. We got down to this and then I froze for ages. I just stopped for so long here. I've waited for ages thinking I can't solve cubics. And I can solve cubics. So this is my lesson 1. I can solve cubics. Here's a cubic, I've solved it. Then I wrote out the cubic. It's an embarrassing amount of time to actually write the cubic down. So I've got to work on that. Just write stuff down and then let my brain process it. And then I pulled out the factorial 1/2. I lost confidence because I wasn't really sure if 1/2 was a factorial, was a root or not. I've just got to get on with it. I've just got to sort of focus on this sort of operation, because I'm done if it works. So I need to know 100% that I'm doing it correctly, and that's a confidence thing. You saw me 5 minutes ago try to factorize it and then just sort of stop and rub it all out and not rewrite it. So knowing that 1/2 will work. I tried plugging it in a couple of times and I got different answers each time I plugged in 1/2, so I've got to work on that. Squaring and cubing seems quite slow for me at the moment. And yeah, and then I had a quadratic and I was done. I need to try and get to this bit where I felt happy again because I got down to the thing and I'm done. I need to make sure that I can solve cubics. I'm not scared of cubics. I will write one down and look for roots. I need to practice that kind of mechanical thing, I think, of plugging in 1/2. While also talking to the live stream and doing content. Right, good, okay. Midway through the algebra, I learned that Warwick's doing the same thing as me. Good, what are they doing it at Warwick? Okay. What's the rest of this question? Let's read it. Given that, and then there's this 4 sine squared x plus 1 is 4 sine squared 2x. Is that for all possible values of sine x? Oh wow, what a great fact. Is it true? It looks like it could be true. Is it true though? It's a good fact. For all possible values of sine x, giving your answers in the form. Oh no, fine. What? What on earth is going on? What on earth is going on? Find, not for. Lesson 2, I can't read. Hey, my name's James, I'm 32 and I never learned to read. Give your answer in the form P plus Q root 5. Okay, good. And there's a hence coming up, I see. It's one of those ones where you do a find and you do a find and then you do a hence. What are we doing today? Okay, I would like to spend 5 minutes. I know I've run over. 5 minutes to 5 minutes to plug us all together. I know it looks like I'm writing with a mouse, but I've actually got technology. Isn't that embarrassing? This is my handwriting with like assistive touchpad, everything. I don't know, it's something about the way I write as well makes it look like a kind of deliberate slowness. Makes it look, it doesn't look like the coordination of someone who is using an actual implement, does it? Hi, my name's James, I'm 32 and I never learned to write. I'm having fun. Okay, I'm not going to do that part. I'm going to think about the last part briefly. What is this? So would it be just, I hope it would be something to do with the 18 degrees thing. I can't see any 4s. What is going on with this question? So maybe, So maybe if I use some of these 18 degree things, it doesn't feel realistic. I could just guess 18. Oh, I found some 4s, I think, or something. What if I could make this be something nice? So this is thinking about 18 degrees, and then 5 times 18 would be 90. This would be 1, and I would then be looking at something that looks quite a lot like this line. Not quite, because of the 4s. What if I make that 1/2? So if sine 5 alpha is 1/2, then, no, just like magically, then I'd be solving for 3 alpha plus 1 would be 4 sine squared 6 alpha, which would be an example of the x and the 2x thing going on, because 6 is double 3. That would be nice. It'd be a lot of coincidences, right? If I could find alpha such that this first thing was true, and also such that the alpha matched up with that. I reckon that's probably what's going on with this question. Homework, fill in all of the gaps, do all of the numbers. We are going to call it there, I think. This has been, well, it started out pretty chill. I'm not sure if it's still chill. Definitely we haven't reached any kind of higher level of maths understanding. That was fun. I had fun though. I liked this bit with the K's. I liked this bit with the K's. And I didn't like the bits without K. Got a favourite letter of the alphabet. But I didn't know I had. Good. Okay. Might do this for a bit. It feels like more directed than just random stuff. Maybe I'll have to do a bit of random stuff. Yeah, okay, that's the plan. We do a little bit of random stuff, but maybe not 2 hours of random stuff, but a little bit of random stuff, and that'll also throw off Cambridge from the Senate. Should we look at 2012 next week, or do I want to keep going? How do I want to run this? There's so many questions. The script's also quite long. For example, we've only really looked at 4 of the questions out of 13, or 12 if you 12 if you skip one. I think I'm going to stick on 2011. You know, I think I'm going to stay here and have a look at other stuff. People are not going to like the mechanics stream. Chill stats. Quick look. It's probability, isn't it? Probabilities. Ooh, like it. Okay, this is a good setup. Match ends, otherwise the match continues with another game. Ooh, a series of games. 3 points. Okay, whatever. Yep, good. I get some probabilities. There's probably some geometric sums. Look at this 1 over 2 minus p. It's maybe some geometric sums. And then, oh my goodness, another stats question that's all about skewness. And how to work it out. Oh my goodness, this looks fine. You know about E of mu squared. Yeah. Ugh. Ugh. Okay, this looks hard. Good. Are 2 straight lines with slope I both perpendicular and parallel to each other? So I guess they're saying that they're parallel because they've got the same slope, perpendicular because their gradients multiply to -1. That is amazing. That's really fun. That's excellent content. I'm not sure what it means. I think your rule about multiplying numbers together to get -1 and that meaning perpendicular, that's hard to generalize into higher dimensions or higher dimensional spaces. But I love it as a kind of bit of slightly mad observation. That's really good. There's a good meme setup. Do I still go into schools to do speeches like Quest for the Quintic? Yeah, I've only actually done Quest for the Quintic once or twice. Once? Twice. I've done Quest for the Quintic twice in schools. First time was alright, second time was a bit weird. It's thrice shy in the chat. One of the people from chat was at the second one, which went a bit weirdly. Last time on the stream, we just talked about how weird a presentation it was. But yeah, I still do school visits. I've got a couple coming up this week. Who knows? Maybe I'm going to somebody's school this week. The way people try and arrange that is they contact. There's a thing on my website, or people just email. Or people email undergraduate admissions, or people email the front desk, or things end up at me. When I started, my original job was job description was sort of do things with schools. And then in the pandemic, yeah. Cool. Yeah, where am I going this week? I'm going to somebody's school. Oh yeah, because somebody got in touch and invited me. They were like, we're running a maths club and we need people to come and talk at the maths club. I'm like, I do a maths club. They said, can you come on a Thursday? And I said, no, that's when my maths club is. And then we worked from there. Fun and games. I love that I thing. I'm going to write that down. Hang on. This is just, it's brilliant and cursed. So line 1, y equals ix plus 3. Line 2, y equals ix plus 7. And they're parallel because m1 equals m2. And they're perpendicular because, and I'm putting because in quote marks, m1 times m2 is minus 1. That's just brilliant. That's from Neutrino. I'm going to spell neutrino wrong. Neutrino, you have a 1 and an underscore. There you go. Good. Right. Okay. We'll leave it there. I think. Have a good Sunday afternoon, and I'm back. I think I'm back next week. We will see. If I don't turn up, Cambridge have got to me. God, we've got to work on the beef element of this. Right. Take care, everyone. That's me looking for the button that turns it off. I have not yet found the button that turns it off.